there are established analytical, semi-analytical numerics to solve this type of equation, and rigorous mathematical analysis to discuss about existence, uniqueness, etc. also is possible. Okay. So now in 1D model, I just, one of my master students had done this. It's very easy to plot. So if lambda by d is 1, then it with time, how with time, that means both diffusion and proliferation are same order, then what will happen? After some time, the death takes place, the population reduces. So as t equal to 4, the population is reducing. If you take t equals to 10, further the population goes down. On the other hand, if you take lambda by d equal to 1, greater than 1, less than 1, suppose lambda by d is greater than 1, that means it's diffusion dominant. So the proliferation, the killing is less. So the population is more. But ultimately it is 1 because of our boundary condition. If you give a free boundary condition, then you will have a varied at r equals to 1. But unfortunately, or we are forcing that whatever the growth inside on the boundary, it should be 1. Therefore, all the curves are coming to be 1. Okay. So this is one can easily plot and then discuss. So now slowly we have to understand little more complicated growth models. See, this is the image reconstruction of brain tumor. Okay, this is called glioma tumors. It's not an experiment actually. It is the images are taken on various cross sections of the brain tumor and reconstruction is done. So you can see the density inside. So depending on the color gradient, the necrotic core, the inside color gradient indicates the necrotic core. So how it is varying, etc. So that means slowly with the computational power, one can use experimental and computational together to do such image reconstruction and analyze some things and then forecast. So that is possible. So now, how do you incorporate chemotherapy? So same fiction diffusion models are considered. Now we are adding chemo. The immediate question one should ask, why we are taking negative sign? Why not plus? See, if you give chemotherapy, the population of the tumor cells will increase or decrease. Naturally, they will decrease. See, any cancer patient is taking a lot of pain and going to chemo. Why? Because chemo will kill the cancerous cells. So therefore, somebody is going for the chemo. Therefore, we are putting minus sign here, where GT is the chemotherapy treatment. See, temporal profile, of course, it is a function of time. Okay. So this is the chemo. So now the model is slightly complicated. You can solve numerically. So try to understand what is the growth mechanism, etc. So things can be understood little. But the real scenario of the tumor is not such a simple structure. I have already shown you it's very complicated. It does not have only the cells. It has some pipe-like vasculature, some interstitium spaces. Then there are several macromolecule, nutrients, etc. So how do you model? And one more thing is, we should be interested in the growth control. We should be interested in the growth control. So, it's in the complete structure. The dynamics have to be captured. So now we are slowly introducing in tumor environment. You have H plus ions. They are also transported. So that means we are introducing cells, ions, extracellular matrix, more than one component. All the models here so far, we are talking about one component. That is nothing but only tumor cells. Now here, we have more than one component. That is, C is the cells where maybe there is a typo. Let me see. So H plus ions, yeah, that is H plus ions. Okay, this has a rate, and gamma is degeneration of the extracellular. So that is nu. Okay, so nu is the cells, ions, extracellular matrix, and corresponding growth rate, death rate, etc. So for the cells, we have lambda, and for the ions, delta. For the extracellular matrix, we have gamma as the corresponding growth factors. So now this system is coupled. We cannot obtain any analytical solution. If you want to solve, no doubt it is a dynamical system. No doubt it is indicates the evolution of several species inside an environment, but it's not possible to solve analytically. For example, similar structure can be modeled slightly and with the change parameters of a population in a forest. For example, you're talking about tigers, you're talking about buffaloes, okay, and you're talking about fox. What is the population in a forest? Each will depend on, one is a prey for the other, okay, one is predator for the other. So these are the relations one has to understand, adjust the signs, combinations, all those things. Then you will get a dynamical system model. Okay, so it's an evolving, like evolution of mathematics. These models are evolving. You have to understand the dynamics, evolve a model, test it, working. So then again you improve. So it's a continuous evolution. So now I am introducing little more generic model. So due to paucity of time, I will not spend much time on this. So now cells and extracellular fluid, complete fluid mechanical model. We are discussing as two species. One is the cells, another is extracellular. And in order to understand this, you should know a little bit of fluid mechanics. These two are conservation of mass. These are the conservation of mass, where phi denotes the density and Vc is the velocity. Okay, and V is the velocity of the extracellular fluid. And this is the source and sink. And what is the constraint here? The constraint here is the net population, net cells, and then extracellular fluid is 1. Okay. So then what is the corresponding dynamic model? Velocity of any species is proportional to pressure gradient. Okay. So now we are talking about fluid model inside the tumor. So this is not applicable to population growth, etc. We are now treating how the cells are migrating as a fluid and extracellular matrix as a solid. It's a two-phase model. Okay. So this is called a Darcy equation. And for another phase, if you bring it, so the relative velocity is proportional to pressure, where K is called permeability, mu is viscosity. Okay. So now momentum balance across the species. So this is a Darcy equation only adopted. That is a momentum balance. For each species, one momentum balance you can fit in. Then try to solve. So what is the oxygen transport model? Oxygen transport model is a typical diffusion model. Okay. So this is the diffusion flux and this is the consumption. Due to various factors inside, oxygen is consumed. So it's a simple Helmholtz type equation if it is constant. So the coupled model with a 1D case, I'm just indicating. It's a two-compartment model. The first compartment is outer region within L of t or X of t, and from the origin to L of t is another compartment. Remember, L of t is varying with time. That means the interior necrocortic region of the tumor is growing with time. So capturing that is very difficult. It is a moving boundary value problem. Why? Because this boundary is moving. So this is formulated as a moving boundary value problem, and one can see the boundary condition at r equal to xt is velocity equal to dx by dt. So this will bring in the complication. You cannot simply solve it because it's you will get a equation for x of t. So that is solved. So then with time, how the tumor boundary is changing. Okay. So the interface of the boundary is changing. So that can be captured. So this is not my work. It's available. Okay. How the necrotic core and how the boundary is changing, that has been shown here. Okay. So we have also done something on biphasic mixture model. Okay. So here we are moving ahead with a similar two-phase flow model, and then corresponding fluid mechanical system, and you can solve the equations. I'm not discussing the math. So it's a simple, but it's coupled. So if you write for 1 dimensions, you can solve and discuss. You can identify with time. We are assuming a radial symmetry tumor. That means it's a ball. So inside the ball, how the tumor growth is happening, nutrient molecules are transported. So deep interior, okay, when R is 0.1, so the pressure is high because there are less macromolecules. Whereas when R is 0.9, towards the periphery, the pressure is low because you have more macromolecule transport. Then how the nutrient is transporting from tumor interior to the boundary. So that has been estimated. So based on that, for various parameter combinations, no time, I cannot explain all the parameters. So we can say, let us say this region is necrotic region. That means low nutrient concentration is necrotic region. So this analysis will help us to identify what is the necrosis region. And this is some comparison with the clinical study that we have done. Those who are interested, they can see in this journal. Okay. So yeah, these are some of our works. So those who are interested, they can see. Thank you. Thank you very much. I'm sorry that I could deliver like this. Apologies. I cannot hear anything.
Sir.
Yeah, I'm able to hear.
Respected sir, thank you very much for your able to hear, sir?
Yeah, I'm able to hear.
Audible, sir?
Audible.
Hello? Sir.
It is audible, sir.
Thank you very much. Thank you very much, sir. Yes, sir. Thank you very much, sir, for your excellent lecture, highly thought-provoking on Ramanujan's birthday, giving a lot of information and a new direction to the people who are working in fluid dynamics. Really speaking, this is a different new area which all the research of fluid dynamics along with the idea of solid mechanics, also they can go further and further. You have discussed several models on solid tumor modeling, 1D models, 2D models, two-phase models, etc. The various types of model, and ending with the biphasic mixture, which contains the Darcy's law and other things. So very, very nice lecture, sir. We are very much grateful to you, sir, for your kind gesture, for accepting the invitation in the very shortest period. This is only possible with our head of the department, Madam Venkatalakshmi Garu, for arranging this program. I think all the participants for research area, which all people now can try a lot of this area. So thank you very much, sir, for your kind gesture. We are very much grateful to you, sir. As president, I thank you, sir.
Thank you very much. And due to paucity of time, the notice has come in a short notice, so I could not prepare a much more robust content. So I hope participants find it little useful. I could not connect anything to Ramanujan's works, etc., because I don't work in that direction. I hope you enjoyed a little bit. Thank you.
All the participants clarification from the renowned greatest personality, Professor Rajశేఖర్.
Yes, sir.
Thank you very much, sir. And may I request the next resource person to kindly deliver the lecture. Before that, Manjula, faculty of Mahila University, will give the biodata in brief of Professor Keshav Reddy Garu, Anantapur. Professor Keshav Reddy, sir, namaste. Sir, Professor Keshav Reddy, sir. Sorry. Unmute లో ఉందండి. Are you able to hear? Sir? Are you able to hear? Okay. లైన్లో వచ్చేస్తాను నీకు. లైన్లోకి రావాలి సార్, రావాలి కదా. నీకే ఫోన్
సార్ పోస్ట్ యూనివర్సిటీ వాళ్ళు తీసుకొని నేను ఫోన్ చేస్తాను సార్. ఇప్పుడే చేస్తాను సార్. 2 minutes సార్. ఓకే
సార్.
Yeah. So I think now I am audible. Yes, Venkatalakshmi. Now I think I am audible. Yes, it's audible. Srinath sir. Srinath sir.
Yes, sir. Yes, sir. Vinipistan, sir. Yeah.
Yeah, okay, fine. So now it is okay. The host has muted me, therefore I am unable to unmute myself. Yeah.
Sir, sir, namaste.
Sir, namaste,
Keshwari,
sir.
sir, namaste.
Sir, namaste. Sir, namaste, sir.
Namaste, sir.
Srinath,
Very glad. Thank you, sir. Namaste. Very glad to hear from you. We are blessed with your acceptance, lecture, everything. Faculty, Manjula will, sir, give the brief biodata of your CV, sir. Manjula will give, sir.
Yeah, it's only teacher of mathematics is sufficient,
Sir,
Srinath
right.
sir. Srinath sir.
No, sir, you are.
Yeah, only teacher of
We are
mathematics
greatly
is
honored,
sufficient.
sir, to have. Thank you very much, sir. She will speak, sir.
Good evening to all. So today I am pleased to introduce a dynamic personality of Professor E. Kesav Reddy sir, the resource person of this session. Kesav Reddy sir is an eminent and enthusiastic professor in the Department of Mathematics, JNTUA College of Engineering, Anantapur. He has obtained his graduation, post-graduation and PhD degrees from Banaras Hindu University, Varanasi. His area of research is function analysis and currently doing research on how to implement mathematical methods in computer science to solve complex and IT problems. He has a professional experience of over 20 plus years. Kesav Reddy sir has guided around 12 PhD and MPhil degree and currently supervising 6 PhD students. He has published around 90 papers in many reputed journals and authored several books. He also organized a good number of conferences and workshops. Sir has his own Moodle site through which he teaches mathematics to BTech and MTech students online. Kesav Reddy sir was honored with AP State Best Teacher Award for the year 2017 and Distinguished Scientist Award. He also BOS and BOE member of different autonomous institutions. We are glad to hear, sir. Dear delegates, let us welcome sir to deliver his lecture. Thank you, sir. Thank you very much.
Thank you.
I am also thankful to Dr. C. Venkatalakshmi ma'am for giving this opportunity. Thank you, sir.
Thank you, madam. Thank you for giving a nice
Over to sir.
introduction. Thank you for giving a nice introduction. Can I start now?
Thank you, sir.
Can I start now? Okay.
Sir, respected sir, kindly deliver the lecture, sir.
Yeah, yes, sir. Yes, sir. Before that, today, I will speak 1 or 2 minutes about the Srinivasa Ramanujan sir. India celebrates National Mathematics Day today to commemorate the birth anniversary of Srinivasa Ramanujan. Srinivasa Ramanujan sir is remembered for his contributions to mathematics, mathematical analysis, infinite series, continued fractions, number theory. He also discovered his own theorem and compiled as many as 3,900 results independently. And in his short life, Ramanujan sir has a wealth of ideas that have transformed and reshaped 20th century mathematics. These ideas continue to shape mathematics of the 21st century also. At the age of 31, Ramanujan sir was one of the youngest member of Britain's Royal Society and the first Indian to be elected a fellow of Trinity College, Cambridge University. And Srinivasa Ramanujan sir was a great mathematician, a prodigy in mathematics. Srinivasa sir had no formal education in pure mathematics, and yet he made significant contribution to the field of infinite series, number theories, analysis, and fractions. So one thing he always says, that when we say the equations, we are going to solve the equation, we are going to get the answers, but the definition of equation, Ramanujam sir always what he has written, that equation means nothing to me unless it expresses a thought of God. Equation is nothing to me, but unless it expresses a thought of God. I think that thought of God has been given in his equations and in his work. Still, the 133 years, some of the equations, some of the things are unsolved now itself. So this is the thing. And if you see the history, if you see the data, what the says, Galileo died at 21. Galileo died at the age of 21. Abel at the age of 27. Ramanujan sir at the age of 33, and Riemann at the age of 40. So the thing is, the mathematics is for young people. Below the age of 40, the great peoples are there. So what does it mean? So this indicates, the data says, if we are in the age of 40s, below 40 or 40, we are good in mathematics, and you can have an innovative thing. I'm not going to say that 60 years old cannot do mathematics, but there should be some innovation in that one. So this mathematics is a young man's game. So this data shows that mathematics is a young man's game. So now today's talk, it's a great personality. I make a namaskaram to Srinivasa Ramanujan sir, and I start my lecture, that is Riemannian geometry and machine learning for non-Euclidean data. This is just because the title of the conference is something new in the mathematical field. So I have chosen this topic. So Riemannian geometry in this one. Just a minute. Yeah. So it's not working. It's visible to all. I think I have to again share. Yeah, now I will share. Share the screen. Yeah. Now, so the hierarchy of mapping is isometry and distortion free, area preserving, geodesic preserving, angle preserving, conformal type of mapping. So this is the hierarchy of the mapping, that is isometry. And what is meaning of the isometry in mathematics? An isometry or congruent transformation is a distance preserving transformation between metric space, usually assumed to be bijective. Area preserving, a linear transformation. So this is isometry, distortion free. Area preserving is a linear transformation is a linear preserving area preserving of its corresponding determinant has absolute value 1. That is area preserving. Geodesic preserving in mathematics, specifically in differential geometry, a geodesic map or geodesic mapping or geodesial diffeomorphism is a function that preserves geodesics. So geodesic preserving. Angle preserving is in mathematics, a conformal mapping is a function that locally preserves angles, but not necessarily lengths. More formally, stereographic. So more formally, the angle preserving means a conformal mapping is a function that locally preserves angles. So this is the hierarchy of the mapping, what we are going to see in today. So calculus of the sphere, suppose a unit 2 sphere is parameterized as, suppose I say unit sphere x square plus y square plus z square equals to 1. So what are the spherical coordinates we are going to give? Cos theta sine phi, sine theta sine phi, and cos phi, x, y, z. So other coordinate parameterizations are possibly what we can say x, y, z, we can give like this. So what we are going to do with this one, calculus on the sphere. Now, the given curve, we are going to say xt, y, it is z, parameterized now on the sphere. It's incremental arc length. What is the incremental arc length? ds is the incremental arc length, and ds square is dx square, dy square, dz square. And it is going to be related like this, d phi square plus sine square phi d theta square. So we can put it in a matrix form that is like this. So concatenation or multiplication of this matrix will give this equation. So the matrix G is called the first fundamental form in classical differential geometry. So the first fundamental form in the classical differential geometry, and we call it as a Riemannian matrix. Here comes a picture, the Riemannian matrix and the classical differential geometry. So for first fundamental form, the matrix G, we are going to say sine square phi 0, 0, and 1. This is called a first fundamental form in classical differential geometry, and we call it as a Riemannian matrix. So when the length comes in picture, we are going to say, you see the figure on this one, this is like this. So if I say length C, so how to get length? If you are going to the integration of ds, if you are going to make an integration, we are going to get a length. So integration of what? ds. What is s? S is the arc. This is totally here. Now integration from one point to another point, suppose 0 to t, if we integrate this one, we are going to get the length of the total C. And area, double integration gives the area. So if I want the area, I am going to say that double integration dA will give the area. What is dA? Mod of sine phi d theta is the area element. This dA is the element, this one, which is known as area element, is square root of determinant of G, d phi and d theta. So this is how to calculate the length and the area in this form. And the local coordinates here is theta and phi, and the Riemannian matrix we have already defined, that is, this is the Riemannian matrix. Other local coordinates are possible, are also possible, and other choice of Riemannian matrix are also possible. That defines on the local coordinates by defining ds square differently. Okay, for example, if suppose I want to make a 3 by 3, so this is the thing what I can make it ds square dx dy dz as the inputs with 3 by 3, and this is the column matrix. So like this we can have it, this one. So manifold, a differential manifold is a space that is locally diffeomorphic. So that's why I told that when we called about the manifold, the geodesics and all comes in picture, and diffeomorphic to Euclidean space. Example, multi-dimension surfaces. For example, suppose manifold. This is a manifold M. How this one? See this one. This is like this bended. This is the curve. This is a point P. Now I am going to make a tangent like this here, and this is a sheet like this, TP and M. So M is a manifold. So local coordinates are x, local coordinates x. So invertible with the differentiable inverse, essentially one can be smoothly deformed into the other. So we can deform. For example, if you take a paper, if you take a plain paper, for example, curvature, when we study, what is that one? If at any point on the paper you can first direction, and you can make it something what you say, cone, cylinder, but this cannot be happened without bend. So without crumbling or distorting to a get portion of the surface of the sphere. So this is the thing what we are going to get it. So local coordinates are also be in a picture. This is the another thing what we have to see. And Riemannian matrix is an inner product defined on each tangent space. What is that? For example, the same thing continuing. This was the TPM, what we have defined last. Now this is TP dash. Now this is the point P. This is point P dash. Now once again, one tangent we are going to make it here. So what is that? Riemannian matrix is an inner product defined on each tangent space. So these two that varies smoothly over M. So ds square, we are going to say summation over I and j. we are going to get this one. So this is the thing, and this is the final thing what we are going to get it in Rm. So this GS is element of Rm cross M, where M cross M is a matrix we are going to make it, and this is the field. So symmetric positive definiteness is there. Now again in the Riemannian manifold, if I want length, now the thing is different. What is that? When I say length in local coordinates x1 to xm, so length is given by the integral over c ds, and the ds is now differentiation of x, that is x dot t transpose g function of xt and x dot t, this one. This now gives the length. When I say Riemannian manifold, volume is given by so and so integral, and this gives the volume. If you see the shape here, this is c, this is v. Now this is a volume when we see in calculation in the manifolds. So when we say the calculus of Riemannian manifold, at that time the length and the volume will be like this. Mappings between Riemannian manifolds, this is the mapping. Say f is a mapping here. Now see this one and this one. This from this to this is a phi. From this to this we are going to say psi. So this is m and n. F is a map from m to n. Now this ds square gives with double summation, that is summation over I and j with this one, and this ds square is over alpha and beta with this type of thing. So this is a mapping between the two Riemannian manifolds. So given two manifolds, suppose m and n, the mapping already I told you, this f m to n, and isometry I already told you what is the isometry. It preserves the length. So distance and angle everywhere. If it preserves distance and angles everywhere. So if I say the distinct between this one, what will happen? M and n are then said to be isometric. And you see this one, this is original m, this is original m. N isometric to m. N isometric to m, this one, but n is not isometric to m, this one. Why? Because see this, the shape is like this. This is isometric. It is not going, it is preserving the distance and the angle everywhere. So, but not in this case. So this is original m, this is a n isometric to m, this is n not isometric to m. Now, mathematical formulation for the isometric, suppose coordinates here p, we are going to say this is m manifold, and this is a curve c, and f m to n is a map. So when we go from here to here, you see, watch here, this is m, this is n, okay, this is m to n. Now this c we are going to say fc, and this point p is going to say fp, coordinate metric. Now suppose I want to calculate this length, then a to b square root of so and so. L over fc is integral a to b square root of so and so. What we are going to say, these both are isometric. These both are isometric. And the g we are going to put it by this formula, where j is dou f by dou x, partial differentiation of x with respect to x, because it is a member of n cross m, r n cross m. So this is isometry mathematical formulation, and this plays a very important role when we go for a machine learning or artificial intelligence. Now the trend starts from last year. This part is going to be a very deeper and deeper in the machine learning and AI part, this mathematics. Isometrics and Gaussian curvatures. So if you see Gaussian curvature, already I told you. So this is m, suppose this is x1, x2, x3. There is no isometry between manifolds of different Gaussian curvatures. What's the best one can in this case? See, this is the case, and this is R2. Okay. Now this f of x1, f of x2, and f of x3. Sorry, these two are f of x0. So f of x1, x2, and x3. So this is this comes from this one to this one. Now all it is not necessary. There is no isometry between manifolds of different Gaussian curvatures. This is different Gaussian curvatures. So what's the best one we are going to do it for this one? What's the best one we are going to do it for this one? That is finding nearly isometric maps. When it is not possible, we are going to say we have to find a nearly isometric map, that is from this one to this one, that is f m to n. This is nearly isometric. Local coordinates both are there, metric is there, and we are going to say, so minimum of f, so minimizing the case errors, and the nearly isometric maps we are going to make it to make our distance what is that, preserve the distance and the angle, coordinate invariance. Okay, so for example, see this one, see this volume 1 and what this, in old days there was a radios and tape when you got it, this type of buttons for the volume. So this if you see these two, it is coordinate invariance in this one. This was in the 1984 case, this has been done by using this one. Okay, coordinate invariant functionals. Now we came to the functionals. Suppose the manifold is there, the Riemannian matrix is developed. Now this is a physical interpretation of this one. This is x1, this is xm, and this is the J forms, that is J transpose Hj is this one, and this is a F map, and this goes to H, y1 and yn, that is xm to yn, x1 to y1, and this is y equals to f of x. So this is mg local coordinate with x1 and up to xm. Riemannian matrix is G. Here the Riemannian matrix is H. A coordinate invariant functional of m to n, function f m to n, has a general form like this, and where the sigma dot is any symmetric function, and lambda 1, lambda 2, so on, lambda m are the roots. So this is the formula how we are going to see the invariant functionals mathematically. So harmonic maps, then it comes to the harmonic maps. So our harmonic maps, we have an intuition that if we take m to be made as elastic, for example rubber, and n to be rigid, for example steel, what will happen if you make a rubber going to be what you can say, cover the steel, wrap on the steel, what will happen? Let m settle to its elastic equilibrium state. This is the harmonic map solution. This is the harmonic map solution. This has been given by Els and Sampson in 1964. What is the harmonic maps and how it is going to be a harmonic map solution. Now, with the boundary conditions, the sigma is over this one with summation all lambda 1 plus lambda 2, so on, and the boundary conditions are dou n is equals to f of dou m. The harmonic map functional is given by this function, and the variational equation is given by this one. This is important. This variational equation where the Christopher symbol is involved in this one. This variational equation, the first thing what we are to make it, this one a very less and less, because if you want to make a correct type of isometric, this variational equation should be as minimum as possible. So variational equation is given by this one. In some cases we are going to minimize this one, and some cases we are going to leave as a variational equations. Examples of harmonic maps: finding the minimum distortion map from a unit interval, for example 0,1 to 0,1. This maps the interval onto this one so as to minimize d of f with this factor. Minimize d of f with this factor. Variational equations are the double differentiation of f is 0, and it gives the equation for the line, that is f equals to t. So this is the harmonic examples of the harmonic maps. Geodesics: given 2 points on the Riemannian manifold, find the path of shortest distance connecting these 2 points. So what is that? f(0,1) to n with end points specified. So when we minimize this one, variational equation is this one. So what I told you, this should be equals to 0. So nearly equals to 0. Then we are going to get it, the maps correctly and isometry to the point. So this is the diagram for that one. That is f of 0 is p, f of 1 is q, and this is n. And this is from 0,1 to n. Okay. Now, examples of harmonic map, if you see this diagram, So find the equilibrium temperature distribution over a planar region with a boundary temperature specified. That is from R2 to R with value for F specified on the boundary of the region. And variational equation, I already told you, we put it as the del square F is 0, Laplace equation. This is the example of harmonic maps when we see in this one. Manifold learning, if you see this one, a lower dimensional Euclidean representation of higher dimensional data. This is very important when we see a data science, when we involve in a data science studies. From lower, how we can go for a higher data. For example, the lot of data cannot be handled in one place or on one system. So what we are going to do, we are going to take a sample of the data and then we are going to project on the total data. So this is the very good manifold application where we are going to see this one. So for example, this is U belongs to RD. This is RD. This is a F function. It goes to here. Now see this data I have taken. And studying this one, I am going to reflect the total things on RD. We can speak about RD. Examples for locally linear embedded, LLE, and Royce has studied in 2000 this one with his group. See, this is a mapping 3-dimensional data to 2-dimensional space, because if I want to visit visibility of the three-dimensional data, I can reduce it to a 2-dimensional space and I can see what is happening. So face image mapping in 2-dimensional space is like this. Riemannian manifold learning is like this. So from this to this, F is a map. This diagram already I have shown in the previous slide also. This comes from this one and this comes from this one. Or if you have this one, you can go to this manifold, and from this one you can go to this manifold. What is that choosing need to be made? Manifold M and N, metric G in M, metric H in N, integrand functions, constraints, boundary condition, decriticization method. These are all things what we are going to learn in this Riemannian manifold learning, and there should be a roadmap for this. All the things, algorithm is needed for all the things. For example, harmonic mapping, distortion, details. If you see this diagram, you see this one, this is Rn, this is the things. This all are going outside this this one towards outside. So what is that? This D matrix and K matrix play a very important role. What is that? Embedding on boundary points, embedding points in Rn. So this plays a very important role when we go for optimizing the things, or distortion details we are going to study. This plays an important role in this one. So for taxonomy, suppose LLE, locally linear embedded, Laplacian eigenvalue, diffusion map. For this, everything G inverse is specified. This is given as a table, what to do and how we are going to take it. What are the volume element we have to take it. This is taxonomy for all the pseudometric and so on. So Swiss roll examples is, this is the data 2-dimensional manifold in 3-dimensional space, and from this you can have this type of what you say 2-dimensional manifold in 3-dimensional space. You can see the graph like this. Harmonic mapping with boundary dow n to minimize the sigma lambda. So this is the thing what is happening in Riemannian distortion. Okay, so flattered is this one, and this is the thing. So this plays a very important role when we have image processing, or when we are going to study about the data in 3-dimensional. We are going to, suppose it is not fit for me to have it study directly in 3-dimensional. What I do, I am going to take a data, I am going to study in 2-dimensional, and then I am going to extend it to a 3-dimensional, or I say it will work in the 3-dimensional if like this. So these are the things. Face images, for example, face images for the corresponding 2-dimensional embedding. So this is the thing. Mouth shape is like this. Mouth shape is like this. Isomap embedding is like this. Okay, Riemannian distortion is given like this. So these are the things what a very good application of this Riemannian matrix and Riemannian geometry or manifolds is having now these days in the application part. For non-Euclidean data particularly, Kendall shape is like this, M represents Mn like this, and Lie shape is like this. See, these three shapes mathematically you can write like this, but the thing is the shapes are like this. You see, this is B bar, theta is there, N is there. Now from this to this and this to Lie shape. So this is the shape what we are going to see, that is GT. Now this is these two shapes. When we say this, you are good. So it means rotations. SOS means rotations. Rigid body motions is AC. SO is rotations. Rigid body motion is AC. General linear transformation. What is linear transformation and their various subgroups? Example, etc. And what is the things? Geometry, distance metric, well established to well known. So this is the things how we can make it a human. For example, a human being itself is a data. Where if you see particularly we are all stand or made it by a point. If you our eyes are going to join all the points to see a human being like this, but if you see the data is like this, very small data which can't be catched by the eyes. Therefore, when we say or when we see about the ghost, the eyes is not going to catch. But when we say we want to see that one, we have to use some technique such that it should be visible. What does it mean? It's a n-dimensional. I have to reduce into 3-dimensional because our eyes are only going to catch a 3D figure, 3D shape. So I have to reduce into 3D and then I have to see it that one. So this is the beauty when we say, and the n-dimensional, the data is non-Euclidean. So non-Euclidean data is very difficult to control or to study. So inertial parameters of a rigid body. So phi is like this, 4/4. See this one, see this diagram. This is PB, and at B point and at C point, if you see the physics is all, mg is going to be downwards. Okay, weight is going to be work on downward, right? So this positive definiteness matrix I need such that it should work for me. So this is a positive definiteness. This P phi should be positive definite matrix that should be greater than 0 such that to work. So natural distance on Pn, if you see the geodesic path on P4, this is 1. And if you see the geodesic distance between the pairs, that is this one, and see the graph, this is the thing. So this all should be well defined on positive definite matrix, invariant to the reference, dimensionless should be there, and better encoded natural distance between positive mass distributions. This is the thing should be happen. So human, if you see this one, human dynamic model, so kinematic tracking of body links, if you see this one, and existing vector space method is this one, the geometric method is this one. Therefore, we are going for the geometric method rather than going for the vector space method. So this Riemannian metric and this geodesics, or you say differential geometry, now is playing a very very important point in artificial intelligence and machine learning, because we are dealing with the high dimensional system. Because we are dealing with the high dimensional system, we want to reduce the noise in the system. We want to make it something clear. So insufficient noisy measurements are there. How to get it? So existing vector space method, still now we are doing with that one, but now the next stage, the studies are gone into the differential geometry, and the Riemannian matrix play a very important role. When we see this one is clear with the Riemannian metric. So these are the things. And examples of non-Euclidean data, you can say diffusion tensor image, DTI is one of the non-Euclidean data. Okay, and DTI each voxel in a 3D multivariant normal distribution. Okay, so multivariant Gaussian distributions are there, which is involved in this one. So geometry of DTI, DTI is one is this one. What is that? Water molecules are able to move. See here, A, B, C are 3. Water molecules are able to move more easily in the x-axis direction. Therefore, diffusion tensors, this B and C are closer than this A and B. Why? Because they are easy to move in the x-axis direction. Therefore, diffusion tensor B and C are closer than A and B. Using the standard approach for calculating distance and the means, we are going to speak. So some statistics also we are going to use in this one. So I am not seeing the mathematics and statistics different now these days. Now these days, the statistics and mathematics are working together to get some beautiful outputs in the field. So geometry of statistical manifold. So n-dimensional statistical manifolds, if you see, this is a normal curve. So when you go to this one, this is this one, and see this output, this one. It means n-dimensional statistical manifold M is a set of probability distribution parameterized by some smooth continuous varying parameter theta. Okay. Geometry of statistical manifolds, the Fisher has given this information, and this is the calculation mathematically how to get it the manifold, and a connection to KL divergence is through this formula. This is a formula base that we can get it any type. And geometry of Gaussian distribution is given, the manifolds of Gaussian distribution is given in this way, and we say where P is like this and Fisher information matrix is like this. So Euler-Lagrange's equations for geodesics we are going to see, that is these two equations as Euler-Lagrange's equation for geodesic on NN. So geometry of Gaussian distribution. So again, we are going to say some matrix is there. This is a column matrix, this 2 by 2 matrix. And this, you see the shape here. This is like this. This is here, and this is this one. So Gaussian distributions. So distribution has been happened. See this one. So this is the beauty of the Riemannian geometry, what we can do in this one. And restriction to covariances. Restrictions are there. Affine invariant matrix. So invariant under general linear group, we are going to say coordinate invariance, and closed form geodesic distance is given by this one. So what is what I am going to say that rather than having the studies or research, why not we have a research in this field, that how better we can have it a closed form, how better we can have it a coordinate invariance by using so and so. Okay. Results of segmentation of brain, for example, using covariance Euclidean distance is this one, and using M&D distance is this one. See, so why the brain? Because now these days the people are working through data science to study the brain, and to see the every movement, every second movements of the brain. So when I want to read that data is a highly high dimensional data. So to read that one, I need some extra mathematics. So what is that mathematics I need? It means it is above the vector space. It means I need a differential geometry, Riemannian matrix to study that one. So manifold human mass inertial data, manifold learning for human mass inertia data is like this: vector space principal component, principal geodesic, you see this one. So standard deviation is there. So I already told you the mathematics and statistics now these days working together, and we have to work together. It's not like that statistics is not my field and mathematics is my field. No. So statistics and mathematics are working together if I want a something application in AI and ML and in the data science. So these are the things. If you see body thickness captured, height is going to be captured here. So PC1, PC2. This 2 is going to be have here. What is this? Vector space principal component analysis. PCA is this one. PCA is a well-known thing that all engineers are doing, principal component analysis in image processing and all the things. And here, rather than principal component analysis, why not we go for principal geodesic analysis? This is my term, that why not we go for the geodesic analysis? We can get a better output than PCA. This is the thing. So now what I am going to have a remarks for the concluding, that machine learning for non-Euclidean data is receiving greater attention from the ML research community. ML research community, and also number of mathematics people are involved in that one for the application to autoencoders, CNNs for geometric data. Many problems in engineering are analogous to trying to fit a square peg into a round hole. Often the things we work with, which are not vectors, but elements of a manifold. So this is the important point, this third one, which is not a vector, but element of a manifold. This will also work for something magnificent output in the applications. The geometric methods and distortion measures described in this talk can be helpful in addressing such type of problems. So therefore, this geodesic, or you can say manifolds, geodesic and Riemannian metric, I have taken because the title of the conference, the title of the workshop, whatever they have put it, is the recent mathematical trends. So these are the reasons, because high dimensional data is there. So this is purely when you go in the data analysis part, data science part, the high dimensional data cannot be handled with simple type of things. And the vector space is something less for that one. So we are going for the manifold to have it this one. So by this, I conclude my talk. And this is just to make you that rather than going in pure and applied maths, why not we go in this field also as a research, with having some knowledge of the application part, and we can do it a big output by using mathematics in this one. Thank you one and all. Professor Srinath sir.
Sir, namaste sir. Thank you very much sir for excellent lecture. Very, very new area, machine learning, applications of the mathematics, Riemannian geometry, combining pure mathematicians and applied mathematicians and engineers. So this is a very new area, sir. All the participants
Professor
been
Srinath
very
sir.
new area, sir.
Professor Srinath sir,
Sir,
I request
sir.
Professor GP Rajsekhar sir. GP Rajsekhar sir is online. GP sir.
Sir?
GP Rajsekhar sir is online. Sir, GP sir.
Yeah, we will ask him to.
GP Rajsekhar sir. Okay, fine. I think he is not there. GP Rajsekhar sir.
Oh, it seems.
Rajsekhar sir. Okay, fine. Fine. But I want inputs, because GP Rajsekhar sir is also working in the data science. This was the thought what I have given, that instead of going with vector space, why not we go with the geodesic? Why not we go with the principal geodesic analysis? This was the thought. So, okay, sir, I think is busy in some other
This is
way.
highly interesting lecture, sir. Very, very interesting, very new area. People have to work and enjoy the things, sir. Starting with the fundamentals, you said a lot of things, sir. Isometry, everything you gave in a very, very clean, a very nice way. So reading algebra is one style. Reading algebra in the geometric way is a very, very beauty. So you show the figures very nicely, the geodesic distances, fundamental forms, everything you have covered, sir, starting from fundamental to highest peaks, where one has to go through applications to AI, artificial intelligence, and image processing. You very, very nicely gave through very nice examples, phase changing from 2D to 3D, etc. So we are all, it is a fascinating one, sir, seeing how these things are going on, sir. So thank you very much for the nice lecture, sir. May I request the audience to raise the questions, anything, sir. Participants, please, any question you may ask our esteemed resource person, Professor Keshu Reddy garu. Okay. 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 9 Sir, the lecture is very for the
why I have
researcher, sir.
Srinath sir, why I have chosen this one, because the PG students are there, I think PG and
Yes,
UG
yes.
students. What happened? They have differential geometry in their syllabus.
Yes,
for
sir. Yes,
PG.
sir. Exactly.
So
Exactly.
instead of studying like a mathematics, some application part, if they are going to study, it's amazing output and amazing job oriented MSc will be there. So therefore, I have taken this one to speak to the PG students and BSc students, those who are doing in this field.
Yes, sir. Now GP Rajsekhar is on the line, sir. I think.
Sir,
So
GP
GP
sir.
Rajsekhar, sir, you can. Oh, I need to leave the meeting. He said that he will leave the meeting. I think a message has come.
Yeah, okay, fine.
He was not there. So, sir, the Venkatlakshmi should be praised very much, sir. Madam Venkatlakshmi Garu, she has organized this program in a very eminent way.
Yes.
She got a good laurel to the Mahila University. All the lectures are very nice, sir. All the lectures is own beauty. Excellent application, sir. So very nice. I think all the participants have got very rich now new areas for their research. I think definitely they will do the best, sir. Thank you very much. I request the convener, Madam Venkatlakshmi, to speak on this occasion. Yeah. Right.
Let 283 participants registered.
Sir, I mean, sir, one information to the participants and the esteemed experts listeners. 283 participants registered for this program, sir.
Good, very
So,
good.
sir, that is a great achievement for the Mahila University, in particular to Applied Mathematics Department led by the good faculty members. And I think this is the first webinar by this department. And the announcements, I request the convener. Right. Report will be delivered by HOD, Dr. Venkatlakshmi. Please speak, madam.
First of all, I thank Professor Keshav Reddy sir for being a resource person to the today national webinar. Thank you very much, sir. You are readily accepting our invitation within short notice and
Thank
gave
you,
a lecture.
Venkatlakshmi. I
Thank
thank the Mahila University's administration, that is Vice Chancellor, Registrar, and Department of Mathematics total staff, particularly Srinath sir, BOS chairperson for your university, and particularly to the Venkatlakshmi madam yourself. That thank you for giving me this opportunity. Yeah, continue.
Okay, thank you, sir. Thank you, sir. Now I'm going to present the report of the today national webinar. So with blessings of Goddess Sri Padmavati, the Department of Applied Mathematics has organized a two-day national webinar on recent evolutions in mathematics on 21st and 22nd December 2020 with Professor S. Srinath sir, BOS chairperson, SPMVV as president, and myself, head Department of Applied Mathematics as convener, and Dr. M. Shivaparvati, Department of Applied Mathematics as co-convener. On the first day, that is 21st December, the first day of the webinar started at 3 p.m. with inaugural section followed by keynote address and invited talk. The keynote address was delivered by Professor P. Kandaswamy sir from 3:15 to 4 p.m., which focuses on the needs of the new mathematical models to reduce the health and financial problems faced by the society. Later, an invited talk was delivered by Professor B. Maheshwari Madam from 4:10 p.m. to 5 p.m., in which vast number of topics on graph theory and coding theory were presented. The first day section is closed by proposing vote of thanks by Dr. M. Shiva Parvati. On the second day, that is on 22nd December, the webinar started at 3 p.m. with welcoming the participants and resource persons. Two invited talks were given by Professor G.P. Rashekar sir, IIT Kharagpur, and Professor E. Keshav Reddy sir, JNTU Anantapur, on the topics biological tumors and Euclidean geometry, respectively. Both the professors have presented their lectures in an excellent way. The webinar is now drawing to a close. I would like to take this opportunity to extend our sincere gratitude and appreciation to all of you. Thank you. And I'm now proposing the vote of thanks. So gratitude is the key to success and the healthiest of all human emotions. The more we express gratitude for what we have, we will end up having more. So dear delegates, it's high time for me to propose vote of thanks for the two-day national webinar on recent evolutions in mathematics organized by the Department of Applied Mathematics, Sri Padmavati Mahila Vishwavidyalayam, Tirupati. First of all, I would like to profoundly thank our Honorable Vice Chancellor, Professor D. Jamuna Ma'am, the Chief Patron of the webinar, and the patrons, Professor D. M. Mamata Ma'am, Registrar, SPMVV, and Professor S. Nagaraju Sir, Dean School of Sciences, SPMVV Tirupati, for granting us permission with all the support needed for the successful conduct of the webinar. I am extremely thankful to Professor S. Srina Sir, Chairperson BOS, Department of Applied Mathematics, SPMVV, for presiding over this webinar in a successful manner. We especially thank to Professor Srina Sir for bearing 2 days with us, the entire program. Further, I would like to express my sincere gratitude to our resource persons of the 2 days, Professor P. Kandaswamy Sir from Bharatiya University, Professor B. Maheshwari Ma'am from Padmavati Mahila University, Professor G.P. Rashekar Sir from IIT Kharagpur, and Professor E. Keshav Reddy Sir from JNTU Anantapur. All the professors readily accepted our invitation in a very short period of time and delivered excellent lectures. Next, I am thankful to our department colleagues and non-teaching staff for their cooperation. I also express my gratitude to all our participants for your patient listening. Last but not least, I also thank our technical team for their in-time support. Thank you one and all. Thank you, Professor Keshav Reddy sir and Rashekar sir. Thank you, sir. I request all the participants, we posted the feedback link in the chat box. So you will submit once. You will get the e-certificate within 2 or 3 days. Thank you. Thank you one and all. Thank you.